Hi everybody, today we are going to be talking about matrices. This video will consist of 8 parts. First we are going to add matrices, then we're going to work on multiplying matrices, finding the determinant and the inverse of 2 by 2 matrices, and then finding the determinant and inverse of 3 by 3 matrices, along with learning to solve the system of equations in 2 different ways, matrices inverse and Cramer's rule. First, we are going to add matrices, which is a very straightforward and simple process. If we have the following matrix and we are going to add this matrix to it, we are simply going to add the top terms and then we are going to add the bottom terms together. So that will give us an answer of 5 plus 5, which is 12, and negative 2 plus 8, which is 6. And that is our final answer matrix. Next, we are going to multiply matrices, which is a little more complicated. So there's one important rule that you always must follow when multiplying matrices, and that is first write out the dimensions. This one we have a 2 by 2 matrix, and this one we have a 2 by 3 matrix. This tells us 2 different things. First, since the inside numbers are the same, we can in fact multiply these matrices and get real numbers, and our answer matrix will be 2 by 3. So we're going to draw that out. We have a 2 by 3 answer matrix. So first, we are going to be multiplying the first row by the first column. So 6 times 2 is 12, plus 3 times 4, which is 12, and that's going to give us a total of 24 as our first number here. Then we are going to multiply the first row by the second column. 6 times 6 is 36, and we are going to add 3 plus 5, 3 times 5, sorry, so we will have 36 plus 15, which is 51, and that's going to give us our answer right here. And then we have the first row again multiplied by the third column. 6 times 2 is 12, plus 3 times 1 is 3, 12 plus 3 is 15. Now we're going to move down to our second row over here, and we're going to multiply that by the first column. 1 times 2 is 2. 5 times 4 is 20. 2 plus 20 is 22. Then we have multiplying the second row by the second column. So 1 times 6 is 6, plus 5 times 5, which is 25. 25 plus 6 is 31. And then we are going to multiply the second row over here by the third column over here. 2 times 1 is 2, plus 5 times 1 is 5, so 2 plus 5 is 7. And that is going to be our final answer matrix. Okay, so next we're going to learn how to find the determinant of a 2 by 2 matrix. Say we have the matrix A, B, C, D. To find the determinant of this matrix, you are going to multiply the A and the B, and then you're going to subtract the product of B and C. So this is a formula you can use on any 2 by 2 matrix, and we're going to try it out. So let's say we have the matrix 6, 9, -3, -6. In order to find the matrix, we're going to multiply 6 by -6, and we're going to get -36, and then we're going to multiply the -3 and the 9 to get -27. Both of those minuses in the middle are going to make a plus, and we're going to get -36 plus 27, which is -9, and that would be the determinant of our 2 by 2 matrix, and we're going to remember that for our next problem, which is finding the inverse of a 2 by 2 matrix. So say we have the same matrix that we did last example, 6, 9, -3, and -6, and remember that we got our determinant to be -9. We're going to keep that in mind throughout this problem. In order to find the inverse of a 2 by 2 matrix, you're going to do 1 over the determinant, and you're going to multiply that by b minus c minus c a. And notice in the last problem when we did this kind of formula problem, we switched around the a and the b here, and we made the b and the c negative. So it's important to recognize the relationship between the two. And so that means for our matrix up here, in order to find the inverse, we're going to put 1 over -9, and then we're going to multiply that by -6 there because we're going to change those around. And then we're going to make a negative instead of just a 9, it's going to be -9. And instead of a -3, we're going to just do a +3. Then we're going to multiply each of these terms by -1/9, and that is going to give us a total of 2/3, 1, -1/3, -2/3. And that is our final inverse answer. Next, we're going to find the determinant of the 3 by 3 matrix. This is a very long process, and there's 2 ways to go about doing it. I'm going to teach you the more efficient and faster way. So say we have a matrix, and this is a 3 by 3 matrix. We have 1, 3, -2, 3, -2, 1, and 2, -1, 3. We're going to take these first 2 columns out here, and we're going to place them outside of the matrix as well. And now we're going to go diagonal. So we're going to multiply our first full diagonal set, and that is -6. Then we're going to go here, multiply them, and that's going to give us a +6. Then we have these, which are going to give us another +6. And we're going to subtract that from the diagonals going in the opposite direction. So this answer would be +8. This would give us a -1, and this would give us a +27. Now when we add all these together, we'll have 6 minus 34, and that's going to give us -28 as our determinant. Remember that for the next problem. To find the inverse of 3 by 3 matrix, there are 3 important steps. The first is finding the transpose, and this means changing the rows and columns, but we'll get more into that later. Second, we'll be finding the adjoint, which uses the cofactors of the 9 minor determinants, and then we will be using the determinant and the adjoint for our final answer. Alright, so I'm going to explain a little more of what that means. this using an example. So say we have the matrix -1, 1, 4, -6, 3, 4, 2, 0, 6. If you remember from the last slide how to find the determinant, it's not the same problem, but it is the same process. We would be multiplying these together, and that would give us -18. And then we're going to want to write out our first two columns. And then we're going to continue with that process. So we're going to multiply these together, which gives us a +8. These are going to give us 0. So we're going to subtract that from the following, and that is going to give us -10 minus -12, a total of 2. And that is our determinant. Once we have that, we can finally start finding the transpose adjoint, and we can put that together. Alright, so with the transpose, we are simply going to switch the rows and columns around. So this is what our original matrix looks like. And our transpose is going to take this, and instead of it being the first column up and down, it's going to be the first row. So it's going to be -1, -6, 2. This is going to become the second row, 1, 3, 0, and this is going to become the third row, 4, 4, 6. Now we have our first step complete. Now we're going to find the adjoint, which is not a complicated process, it just happens to be a little lengthier. So for this step, we're going to use the transpose. The adjoint matrices always follows this format. It kind of gives the negatives in sort of diamond shape. And it's important to call that out at the beginning. This is going to be 9 tiny matrices inside of our bigger matrix. That's supposed to be a positive. Alright. So first, for this first row, first column, we are going to take our first row and first column here, and we're going to cross those out. Now, what are the remaining numbers? We have 3, 0, 4, 6. Now we're going to move on, and we're going to cover up our next term, cross out whatever is in that row and that column, and we will be left with 1, 0, 4, 6. And then we are going to follow the same process with our 2, and we're going to cover up that row and that column, and we will get 1, 3, 4, 4. Then we're going to cover up our 1. We're going to get -6, 2, 4, 6. Then we're going to follow this exact same process all the way throughout the matrix. -1, 2, 4, 6. We're going to cover up the 0, -1, -6, 4, 4. and I'm not going to continue it through the next row just because I think we kind of have that process down now. Now we're going to go through each of these tiny matrices and we are going to find the determinant, and that means taking those terms multiplied by each other, which is 18, minus those terms multiplied together, which is 0. What is 18 minus 0? Well, it's 18. And we can keep that because there's a positive out here. Now for this matrix, we'll have 1 times 6, which is 6 minus 0. That's 0. And since there is a negative out in front, that means it's going to be a negative 6. 4 times 1 is 4, minus 12 is negative 8. Negative 6 times 6 is 36. 4 times 8 is 8. 36 minus 8 is going to give us, negative 36 minus 8 is going to give us negative 44. When you're multiplying that by the negative out in front, we're just going to get positive 44. You'll follow the same process for each of these tiny matrices, and this will be your final result. And then you're going to multiply this by 1 over the determinant, which was 2. And when you do this, you're going to get your final answer. And that is 9, negative 3, negative 4, 22, negative 7, negative 10, negative 3, 1, and 3 over 2. And that is going to be your final answer. So for this example, we are going to use this system of equations right here, and I also wrote a formula that you're going to use to solve each of these problems, which is right here. So in this situation, our coefficient matrix would be 2, negative 1, 3, 4, 3, negative 2, 1, 6, negative 4. And our variable matrix is going to be x, y, z. Our answer matrix is 5, 6, negative 2. Now, in order to solve for our x, y, and z, all you have to do is multiply our coefficient matrices, the inverse of that, times the answer matrix. So the inverse of the coefficient matrix times the answer matrix. And in this situation, using a calculator, you would get that your answer matrix equals 2, negative 4 sevenths, and 1 seventh, which means that y is going to be 2, or x is going to be 2, y is going to be negative 4 sevenths, and z is going to be 1 seventh. Next, we're going to solve a system of equations via Cramer's rule. So I wrote out some general formulatic things. If we have a system of equations, just like the system right here, these are what we're going to follow to find the x, y, and z matrix. I want you all to notice that on the bottom, we have the same matrix, and this is just the coefficient matrix of our system of equations. However, for our x, y, and z, they're pretty similar with the exception that J, K, and L, the answer matrix, takes the place of the first column of the coefficient matrix for the x, the second column for the coefficient matrix of y and the third column for the coefficient matrix of the z. And you're going to follow this every single time that you use Cramer's rule, and we're about to try a quick example of that. I don't think it's necessary to go through the x, y, and the z, but I'm going to show you how you can find the x. Okay, so for solving any system using Cramer's rule, you really only have to use this to find the x and the y, and then you can plug those back into any of the equations to get the z. In this instance, we're only going to find the x just because you can follow the formulas to find y and z as well, but I want to show you how to do the problem. So first, we will have to find our coefficient matrix, which is going to be 3, 1, 1, -6, 5, 3, 9, -2, -1. And whenever we find our determinant of this matrix, we are going to get -9. We followed this process before to get the determinant, so we should be good with that. And then in order to find our matrix specific to the x, we are going to take our answer matrix, which is -1, -9, and 5, and we're going to make that first in this matrix, and then we are going to use the y's, or I'm sorry, yes, the y's, 1, 5, -2, 1, 3, 1, and we're going to find the determinant of this as well, and that is going to be -2. So -2 over -9, the negatives cancel out, and our x to the system of equations is going to be 2/9.